Hello, I'm Apurv, and with me are Devesh, Kent, and Sinan. We're here today to talk to you about bulk metallic glasses for application in dental implants. To begin, I'm going to go over the background and motivation for this project. As seen in the figure on the right, a dental implant is an artificial root inserted into the jawbone to anchor a replacement tooth. Around 70% of the structural materials used in these implants are metallic, with a titanium aluminum vanadium alloy being the most popular. However, this alloy faces several limitations, including aesthetic issues, cytotoxicity from the release of vanadium and aluminum ions, and a stiffness mismatch between the implant and the jawbone surrounding it. To counter these concerns, bulk metallic glasses have emerged as a class of amorphous multi-component metals that are a promising candidate for dental implants, with a titanium, copper, palladium, zirconium-based bulk metallic glass being our BMG of choice. Moving on to the formulation of our problem. The objectives of this project are to firstly describe the advantages of a BMG over a traditional titanium alloy for dental implant applications, and secondly, to explore advanced manufacturing technologies suitable to commercialize the production of these new dental implants. I'll now hand it over to Sinan to talk about the advantages of our specific BMG.
Thank you, Apurv. Before we move on to the manufacturing process of the titanium-based bulk metallic glasses, we're going to compare the mechanical and corrosion properties of those with the currently preferred titanium-based alloys. So as for the mechanical properties, the bulk metallic glasses have a lower Young's modulus and a higher strength than the titanium alloys, which means they're easier to manufacture and the end results are stronger. The BMGs also have a higher elastic strain and a lower plastic strain and show a 1.5 times higher load to failure, which means they're more ductile and they show plastic deformation before failure, which means the end results are longer lasting. As for the corrosion properties, the BMGs have a higher corrosion potential and a lower corrosion current density, which result in a greater driving force required to initiate corrosion mechanisms, which again goes back to the end results being longer lasting. And these numbers and more show us that the bulk metallic glasses are proven to be more reliable and stronger, and the results last longer, and they should be preferred. Now I'll pass it on to Kent to talk about the manufacturing process.
Thanks, Sinan. Okay, so one of the more commercially available methods for producing bulk metallic glasses is through a substantially modified die casting process. So in conventional die casting, molten metal is injected under high pressure into a mold known as a die. The metal then solidifies, taking the form of the die, and is then ejected, producing the cast part. We can see a conventional die casting machine diagram here. But what does this have to do with producing an amorphous structure and making our bulk metallic glass? The key to this is the high thermal conductivity of the die materials. Die casting has always created rapid solidification rates and is famous for its rapid production rates. Thus, through careful engineering of the die casting process, it is possible to create sufficiently fast solidification and an amorphous structure. So let's move on to the BMG die casting process. As the figure shows, there's little fundamental difference between the techniques. However, the complexity of the system becomes apparent when the details and engineering of the system are examined. Let's start at step 0. Before our process begins, the entire system will be evacuated. This prevents gas entrapment in the melt and therefore porosity in the final casting. In step 1, our alloy is placed within the sleeve and is put under an inert atmosphere, typically argon. A high-frequency induction coil melts and controls its temperature. This keeps the melt at a precise temperature and ensures no unwanted reactions occur. In step 2, the plunger uses hydraulic pressure to force the melt into a water-cooled copper mold. This applied pressure ensures full surface area contact between the melt and the copper mold. This, combined with copper's very high thermal conductivity and water cooling, ensures a very high heat transfer coefficient. Solidification is therefore completed within a few milliseconds. In step 3, after solidification, our BMG is complete and can be ejected from the mold. The resulting BMG takes the almost exact form of the mold as the structure of the liquid has been maintained. In other words, there is no shrinkage typically associated with the phase change. This also eliminates shrinking and contraction-related defects like holes and voids. Now, onto the principal advantages and disadvantages of this BMG forming process. The first advantage is its ability to produce larger volume BMG samples. This is due to the extreme processing conditions, which allow higher, more controlled cooling rates. The second advantage are the more varied shapes and geometries possible. Other BMG forming techniques are constrained in terms of the shapes they can produce. But here, the only limits on geometry are those set by the limitations of mold making. This also leads to the main disadvantage of the process: high initial tooling and mold costs. Consequently, high-performance materials manufactured in complex shapes to high standards of accuracy are critical to this process. In terms of scale, we commonly see shapes with the following dimensions. But in our case, we would be producing rods with a length of 25 millimeters and a diameter of 5 millimeters. While final net shaping is possible with this process, it is generally combined with other post-processing techniques that can form the final BMG part more economically, most notably machining. I will now pass it on to Devesh to discuss this.
So from our bulk metallic glass cylindrical rod, we propose the following manufacturing process flowchart to produce a batch of dental implants. This flowchart consists of individual processes such as machining, which is a subtractive process, various cleaning processes such as vapor degreasing and ultrasonic cleaning, as well as the surface modification technique known as anodizing. We'll go through each of these steps one at a time. So starting off with machining, the machining process is arguably the most important step in our manufacturing process as it requires a high dimensional accuracy and throughput rate. It also necessitates the use of complicated cutting tools to shape the geometry and dimensions of the implant. We propose the use of an automated multi-spindle lathe system, which will be able to address the above concerns. As you can see from figure 5, this system consists of 6 sliding headstock spindles, which allow 6 workpieces or 6 cylindrical rods to be machined simultaneously. It also has a capacity to integrate up to 18 different tooling attachments. So tools such as mechanized saws, broachers, threaders, and other milling equipment can be integrated into this lathe system in order to produce a hollow and threaded dental implant. From our calculations, we estimate that the throughput rate of such a machine will be roughly 9 seconds per implant. After machining, the implant would go through a cleaning process known as vapor degreasing. The part would be placed inside a basket, which would be hovered over a sump filled with a hydrocarbon-based solvent. The solvent would be heated, which would release saturated vapors that would accumulate on the surface of the part. Over time, the vapors would condense off of the part, removing contaminants in the process. This entire vapor degreasing setup can also be considered as a closed loop setup. This is because the saturated vapors that are released from the boiling sump would be able to accumulate on the cooling coils located at the top of the tank. Eventually, the vapors would distillate and condense into a liquid, which can be collected in a separate tank, thus ensuring complete recovery of the solvent. After degreasing, we propose a dimensional measurement process to ensure that the implant meets manufacturing specifications. This is performed via a laser coordinate measuring machine. The implant will be placed inside a chamber where a laser will be projected onto its surface, while cameras will triangulate the changing distance and profile of the laser. This will generate a set of 3D point coordinates, which can be converted to a CAD model of the scanned implant using computer software. After this, the surface of the implant will be treated in order to improve its properties. This will be done via an anodization process, which has been shown to improve the osseointegration of the implant with the jawbone when inserted. The anodization process is an electrochemical technique. So essentially, the implant will be immersed in a 5 molar solution of sodium hydroxide at 25 degrees Celsius. It will be connected to a 3 electrode cell setup to a potentiostat. A voltage will be applied across the implant, which would modify its surface properties over a period of time, roughly 45 minutes. There are several research papers that show that this process helps create a hierarchical nanoporous surface layer on a bulk metallic glass composed of these following elements. Figure 8 shows an optical micrograph of this surface layer. It's roughly 200 nanometers in thickness and consists of various irregularities, such as the one shown here, that mimic the nanoarchitecture of the natural tissue. It is also rich in titanium dioxide, which improves its corrosion resistance of the bulk metallic glass implant. The final step in our manufacturing process is an additional cleaning process known as ultrasonic cleaning. The implant will be placed inside a water bath where cavitation bubbles will be used to agitate the solvent to generate forces on the contaminants adhered to the implant. So after all of these steps, we would have produced a fully machined and cleaned implant suitable for insertion into a patient's jaw. I'll now hand it over to Apurv to wrap everything up.
Thanks, Devesh. To summarize, we established that die casting, followed by machining, anodizing, and ultrasonic cleaning, was a viable advanced manufacturing and processing route for BMG dental implants. Furthermore, the advantages of BMG implants over conventional titanium alloys are strength, durability, biocompatibility, and ductility, making them ideal for forming into implants. In terms of future work, we aim to investigate dimensional tolerances in the industry and standard procedures for ensuring conformity, minimize die casting cost, since that was the most cost-intensive step of our procedure, and optimize the topology of the surface nanolayer to mimic human enamel structure. Thank you very much.